Okay, year 11. I'm about to make a screencastify video on the cubic function, which is 413, which is the next exercise that we're meant to be covering. Now, we're going to do transformations of functions in a lot more depth later on. But this is our first look at it. Well, not our first, because we looked at it with the circle and we looked at it with the quadratic. But here we're going to get a bit of terminology that's going to come up later on, and it's in this bit here. So I've got three constants here. I've got a k, I've got a b, and I've got a c, and they're the way that the constants are going to be written later on. Now, what do those constants do to the graph? Now, if you know from last year when we did the elective that any movement with the x will move it left or right, and anything that goes with the y will move it up or down. This number here, this k here, and we're going to have a look at it, does something else, and we should know it'll make it steeper or flatter according to the value of that number, or in fact turn it upside down if it's positive or negative, or if it's negative it'll turn it upside down from the positive. So first of all, let's have a look at what a standard cubic function looks like. And you should remember this: a standard cubic function looks like this. And we're going to talk about that point a little bit later. And that's y equals x cubed. And the standard negative cubic just goes the other way. Now, it's almost impossible to draw these accurately, which is why when Margaret tells us to solve these things graphically, we're not going to do that. So they're our standard cubics. But what happens when we put some of these values in over here? So we put a k, a b, and a c. Let's have a look. So here I've got a k and a b and a c. And I'm just going to make that 1, so they're all 1. Well, actually, no, I'll make that 0, and I'll make that 0. Come on. And there's our standard cubic. And you can see how steep it gets. Now, if I get this one just to go, come on, put the slider in there. You can see it gets skinnier and flatter, and then when it goes negative, it turns upside down. So if it's got a big number in front of it, it gets steeper and steeper and steeper. So when it's up to 10, look how high it is. That's max, and then it comes down. And then when it goes from less than 1, so let's say, let's get it to be a half. It's reasonably flat. It's getting less steep. If I go closer there, and that's the same in the negative side, but it's just the opposite direction. And when it's really high, it's really steep. So that's what the k does. So let's put the k back to 1, so we just get our standard positive. And let's get this b going. Now that b is with the x, so it's going to do something with the x coordinates. Remember, x is left to right. And as you can see, it just moves the curve from left to right. So the value of b will either be to the left or to the right. Well, let's put that back to 0. That's pretty easy. So it's right on the curve now. This is our standard one. And that's C. Well, that's C. I know it doesn't look like it's with the Y, but if we subtracted it over the other side, it would be. And as you can see, or you can observe, that it just moves it up or down. And an added bonus is that if it's written like that, the C will tell you the Y intercept. Oh, no, it won't. It won't tell you the Y intercept, will it? Yeah, in this case, because X is 0, because B is 0, but if X is another number, it'll change it. All right? So, that's what B, C and K show us. I'm going to explain this a little bit later when we get onto them and we're graphing each of these functions. So let's move down here, and I want to talk about this thing. It's called the point of inflection. Now, the point of inflection is where a curve changes concavity, and that's any curve. So here's our cubic. It's going up, it's concave down, it's concave down, it's concave down, and all of a sudden it changes and becomes concave up. That point where it changes, we call the point of inflection. And it happens for the negative one as well, concave up, concave up, concave up, concave down. And there's a point somewhere there where concavity goes from being concave up to concave down. And we call that the point of inflection. Now, if you're looking at old textbooks or past HSCs, they will call it the point of inflection, and they will spell it like this. I don't know why we always spelled it like that, but we did. But now our new spelling is that, but it is the same thing, the point of inflection, and it's where the concavity of the curve changes. And it's very important in a cubic because you can see it's a point where that curve turns. Righto. So let's have a go at some of these. And first of all, X and Y intercepts. These are pretty easy. I'll do 1A and 1F. So 1A, y equals x cubed minus 1 when x equals 0, y equals 0 minus 1. Oh, y equals minus 1. That was pretty easy. And when y equals 0, if we let y equal 0, we get 0 equals x cubed minus 1. Take the 1 over. 1 equals x cubed. Cube root the 1, and we get 1, x equals 1. So the x-intercept there and there was pretty easy. What about at, and I might do more than just 1A and F. I'm just getting the answers up to make sure I'm not stuffing them up. I'll do B, and then I'll do F. So B, we've got, oh no, I don't want to do B. I wanted to do one that would give me a negative. Let's do D. And I get y equals negative x minus 4 all cubed. Well, when x equals 0, I get y equals negative 0 minus 4 cubed equals negative 4 cubed. Negative 4 cubed is negative 64, and I've got a negative out the front, so it's positive 64. Hopefully you would have done that on your calculator. Now, when y equals 0, I get 0 equals negative x minus 4 cubed. Well, divide both sides by the negative. 0 divided by negative is just 0. X minus 4 cubed. Now, I don't need to go any further. I can cube root 0 and add the 4 over. I can just go, well, that's just x minus 4 times x minus 4 times x minus 4 times x. So that means what makes that 0? X equals 4. So there's your x and y intercept. F. If I have a go at F, and you have a go before me, y equals x minus 2, x minus 1, x plus 5. Y equals x minus 2, x minus 1, x plus 5. Now if I let x equals 0, if I let x equals 0, I'm going to get y equals, well, 0 minus 2, negative 2. 0 minus 1, negative 1. 0 minus plus 5 is 5. Oh, y is going to equal 10. Now, if I let y equals 0, I get 0 equals x minus 2, x minus 1, and x plus 5. And straight away you should be thinking, well, that's how we solved quadratics, but we only had 2 of them, and we just had to find the values that would make that equal 0. Yeah, so x will equal 2, x will equal 1, or x will equal negative 5. Okay, so there's how you find the intercepts for those questions. Now, let's have a look at question 2, because it's the most important one, I think. Drawing these. So to draw these, and it's very hard to draw these accurately, which is why when they ask you to find graphic solutions to some of these, you can't. So I'm going to ignore that question when it comes up. Rather you try and do it algebraically than do it graphically, because you can't do it graphically, not unless you're a really good drawer. Okay, so let's have a look at the first one. And I'll get myself a set of axes. And what have I got? Y equals negative x cubed. Well, we already know that that is just that. There's y equals negative x cubed. 2x cubed will be steeper. The next one, y equals x cubed plus 1. So C. Again, get myself a set of axes. So x cubed plus 1, it's just going to move it up 1. So it's going to come up here and go like that. So I know that's 1, and I could solve that. Y equals x cubed plus 1 when x equals 0, y equals 1. Okay. But to find this point here, I have to let y equals 0. And I get 0 equals x cubed plus 1. Well, minus that 1, minus 1 equals x cubed. Now, we can't find the square root of a negative number, but we can definitely find the cube root of a negative number. In this case, it's just negative 1. So that point is negative 1. And I'll show you the cube root of negative 1 is negative 1. Okay. So some of these are harder. I'm going to do D, E, G, and then F. Oh, I have to do I. You can go and have a go at them. And remember, you can always check them on Desmos. So here's D. So D. Y equals x plus 2 squared. Well, if you remember from that Desmos, y equals x plus 2 cubed. If it's with the x, it's going to move it left or right. Now, how do I know? How do I know whether it's moved left, or how do I know if it's moved right? I look at that and I go, what's going to make that 0? And the value of x that's going to make that 0 is -2. So -1, -2. So this graph has just essentially moved left to the 2. So it's coming there. That's a bit bad. Now, I know that spot, but how do I know this spot? And if I let x equals 0, I'll get y equals 0 plus 2 cubed, which is just 2 cubed, and that's 8. Now, as you can see, that doesn't look like much scale. That's badly drawn. If I was going to do it properly, I should have been going much, much higher. So that's what I mean when you're trying to draw these, and you can have different scale on different graphs, on different axes. Okay, so that was pretty easy. Just move it. Let's have a go at E. Now, E, and that's y equals -x minus 3 cubed plus 1. Well, this is going to be a negative parabola, so it's going to look like that. And which way is it going to be moved? Or what makes that 0? It's going to be moved 3 to the right and up 1. So 1, 2, 3, and up 1. Okay, so it's going to look something like that. And even that's poorly drawn. I'm going to do that again. And the intercept is going to be somewhere up there. Now, how do I find that? Well, let x equals 0. And I get y equals -0 minus 3 cubed plus 1. Well, that's -3 cubed plus 1. And that's going to be 27 plus 1. Oh, 28. So that value is 28. This value down here, the x-intercept, I have to let y equals 0, and I get 0 equals -x minus 3 cubed plus 1. Minus 1 equals -x minus 3 cubed. Divide by -1, 1 equals x minus 3 cubed. Cube root it. Cube root of 1 is 1. X minus 3. Add the 3. 4 equals x. So this value is 4. Right. So that was a difficult one. And this point here, this point of inflection, is 1 and 3. And we've just transformed them. Sorry, 3 and 1. And we've just transformed them. Okay. I want to have a go at G, and then I want to have a go at F, and I want to do them in that order. So G is a positive cubic, and this is where you don't need to be as accurate. So G, y equals x plus 2, x minus 3, x plus 6. It's a positive cubic, so it's going to look like that. And all of a sudden, you haven't seen these before, but you're going to get lumpy bits. You're going to get turning points. You don't have to find these, and they're not symmetrical. So let's find some things out. When x equals 0, I'll get the y-intercept. Well, when x equals 0, y equals 0 plus 2, or 2, 0 minus 3, or minus 3, 0 plus 6, or 6. Oh, negative 36. All right, so negative 36. Wow, way down here. What about when y equals 0? Well, that means 0 equals x plus 2, x minus 3, x plus 6. Oh, well, that gives me x equals negative 2, x equals 3, and x equals negative 6. Oh, 1, 2, 3, 4, 5, 6, negative 6. 1, 2, 3, and negative 2. That means that this curve does something like that. Now, you cannot be expected to find that, and it's not symmetrical. And you can see they're trying to do a freehand diagram, and when you look at the answer that they've got in the back of the book, their scales are all over the place. Even here, my scales are bad. And you're not expected to draw it exactly to scale, because when you cube a number and it gets really big really quickly, you can't fit it on a page. So down here, where Margaret asks you to find in question 5, 6, solve these graphically, you can't, because you can't draw the graphs accurately enough. So let's do this last one. And the reason I wanted to do it is because it's negative and it's got a 0 on it. You go and have a go and see if you can do it by yourself. No. I've got another one there, so it's okay. So y equals, actually, I'll do it over here because I need space because it's a negative cubic. Y equals negative x plus 2, x minus 4. Well, when x equals 0, y equals negative 0 times 0 plus 2 times 0 plus 2 times 0 minus 4. And I don't even care about those because I've got 0 times it, so it's just going to be 0. So there's my first big one. I've got a 0, 0. Now, when y equals 0, you get 0 equals x, negative, x plus 2, x minus 4. Well, when all these three things equal 0, so when x equals 0, which we already know, when that equals 0, which is x equals negative 2, and when that equals 0, x equals 4. So over here, negative 1, negative 2, and 1, 2, 3, 4. It's a negative parabola, and it's going through here and here, and it's not symmetrical. So it's coming down here, goes through there, turns around again, goes down there. And you can see how hard it is to draw these accurately. All right. I want to do the last one. I want you to go and have a go at it, but I'm going to do it. And the last one is going to bring home a very salient point in pointing out to us double roots. So, what have I got? I've got y equals x minus 1 x plus 3 squared. Well, when x equals 0, so this is a positive parabola. When x equals 0, y equals 0 minus 1 times 0 plus 3 squared, which gives me minus 1 times 9, negative 9. So it's going through negative 9, somewhere way down here. I'm not going to draw it to scale. Now, when y equals 0, when y equals 0, I get 0 equals x minus 1 x plus 3 squared, which means x equals 1 or x equals negative 3. Okay, so 1 so it's going through here and here, but it's got to look like that, and it goes through here. So how are we going to do that? Now, you're not meant to find where these lumpy bits are, but this thing here, it's what we call a double root, and a double root is a turning point. We're going to explain it later with calculus, but a double root will be a turning point when it's written like that. So this curve comes up and it hits that point, it turns around. And then it comes down here, goes through 9. Oh, jeez, I'm doing that again. And we don't know. I've got a sneaking feeling that it's going to go like that. Like that. We don't know whether that turning point is on the left-hand side or the right. I'm pretty sure it'll be on the left-hand side of that, of the axis. Now, you're not meant to find these turning points, but that's a really important thing, knowing that a squared is a double root. So here, when you're looking at h, that's a double root as well. So it's going to be a turning point when x is 0. Okay. Let's have a look at question 3. Now with these, this is going to be hard. Now remember what happens to the curve when we put something with the x, and what happens to the curve when we put something with the y. So if we put it with the x, it moves it left or right. If we put something with the y, it moves it up or down. So here we go. Come back here. Find the point of inflection. Well, remember, this number just makes it steeper, whereas this number moves it up or down. And if I were to draw that really quickly, it's just a really steep version of that. And now my point of inflection is at 1, 0, 1. It's at 0, 1. There's the point of inflection. It's just moved up 1. Here, it's a negative, but it's moved up 27. So the point of inflection, 0, 27. Here, I've shifted it. Which way have I shifted it? You think about that. Which way have I shifted it? What makes this thing equal 0? Well, negative 2. All right, so it's shifted negative 2. So it's a curve, it's a positive parabola. And here's my new point of inflection, negative 2, 0. Okay, the last two here. That 2 just makes it steeper. It's shifted which way? Well, what makes that 0? What makes that, 1. So it's shifted 1 to the right. So if I get another one of these up, there we go. If I get another one of these up, get out of there. And it's moved it 1 to the right and 1 up. So it's just done something like this, and it's negative. It's negative, so it's coming down. Now, they're not asking you to sketch it or to find the intercepts, but the point of inflection is 1, 1. Now, sorry, I was looking at this, and I've messed that up. Sorry, I was looking at the wrong one for its movement in the Y. So it's moved it 1 to the right and 16 down. So 1 to the right and 16 down. So way down here. And this one's a positive parabola, so it's coming up a positive cubic. And I don't need to find them. All I'm worried about is this baby. So 1, negative 16. The last one, you have a go at it. Have a look. What makes that 0 and how far has it moved up or down? And if you went, well, that makes that 0 is negative 1 and it's up 1. And it's a negative parabola. And this is the point we're worried about, which is negative 1, 1. All right, so finding the point of inflection. What else? Find the x and y. Well, that's just solving that. I'll let you do question 4 on your own. You just have to solve them. Describe those functions. I'm not that fussed. Do not do question 6. Do not do question 6 graphically. You can't. Here, and I'll give you an example of why. Okay. If I try and draw y equals x cubed minus 5. So it's a positive parabola, move down 5. 1, 2, 3, 4, 5. So it's doing something like this. And they're saying that if that is y equals x cubed minus 5, they want you to find when that equals 0. They want you to find that bit there. Now, from my graph, what would that be? 1 a bit. I don't know. And you can't draw these accurately. What you can do, though, is you can solve x cubed minus 5 equals 0, x cubed equals 5, x equals the cube root of 5. So the cube root of 5, 1.7. Now, could you get that from drawing a graph? You'd have to be very accurate. And even then, when you're drawing a cubic. So I'd rather you try and solve them algebraically. All right? And they're not that hard when you do that. These worded questions, I want you to have a go at them. And get back to me with any questions where you found it too difficult.